the end of every table, you're more than welcome to use them.
Thank you.
So if you want to, whoever's at the end of it wants to pass them down, you guys can snag some. They're 4x6. Oh. He got you the big ones. He got you the 4x6 ones. And you can use the front and the back. So, all right, a couple things about the test before we start reviewing it. The first three questions are as they are in the practice ones, just changed a little bit of numbers and stuff like that in them, but they will be the chapter 6 stuff. Questions 4 through 10, the practice test, they were in order. The actual test will not be. So they were in order so you could practice them and get them down, but the actual test will not be in order of the actual sections. So they will be mixed up. And I don't believe, I did not put one of the trick problems on the actual practice test where you actually could use substitution, but it looks like something else. There will be, as I said, there will be one of those on the actual test. So you can do it the hard way. It's fine. There's just an easier way to do one of them.
Will it look similar to the one we went over last class?
But yeah, kind of like that. Yeah. So it should be, you should be able to recognize it. If not, then I've done something wrong explaining those problems over and over again. All right, let's look at the chapter 6 stuff, the volume. I didn't put one on there just looking for area under the curve or between two curves because in essence you have to do that to do the volume anyway. So I just did 3 volume problems. So we're looking for the volume of a rotated region between these two curves. So we've got the blue and the red. So when we're looking at that, we're rotating this around x equals 1. So the radius is going from here to there. Yeah. That's the black line's -1. That's okay. I'm like, wait, did I? No, yeah. So we're going from the radius of the x is -1 to the thing. That was one of the mistakes that I saw in a few people who actually emailed to me. They were adding the 1, or I mean, they were subtracting the 1, where you should have been adding the 1. Because you're looking for the radius. So the radius of this part right here, that's 1, and then it's plus the part that's over on this side over here. So my blue radius, which would be my right, is, this one was the, I gotta remember which one was which. I didn't write them on there. One minus y squared. Yeah. So it's 1 plus 1 minus y squared, which equals 2 minus y squared. And then my left is 1 plus y squared. The next thing you have to figure out is where do they intersect? You could do this on Desmos. If you do it on Desmos, you get 0.707 and negative 0.707. That should be a number that is familiar to you. That right there is the same thing as square root of 2 over 2. So square root of 2 over 2 is the 45-degree angle. So that one comes up quite often. If you had set them equal to each other, you could have solved this the exact same way. So we could have done y squared equals 1 minus y squared. So 2y squared equals 1. Y squared equals 1/2. Square root of both of them, so y equals the square root of 1/2, which is square root of 2 over 2. So you could set them equal to each other that way too and find the answer as well. So if you get a decimal or something that looks kind of crazy on Desmos and you can set them equal to each other and it works out nice, you can. If you use 0.707, you're not going to get the answer wrong. It's just might be a little bit messier to clean things up at the end. y squared plus y squared when I brought over the other y squared. So I added y squared to both sides. And then I divided the 2 to get the 1/2. So most of these problems, you're going to have to figure out where they cross to be able to find that information out. The other thing you should notice on this one is that the top and the bottom is symmetric. That definitely is going to make your life easier if you have that information. Because now I only have to do half of it, so I can do 0 to square root of 2 over 2 instead of the negative to the positive and have to do that information twice.
Just to clarify, the 0.707, those would be intersection points.
Yes, that's the intersection points. So that's actually, if you do square root of 2 over 2 in your calculator, you get 0.707. And anybody in electrical engineering or anything else like that, 0.707 comes up all the time because that's your RMS value of both the electricity that comes out of your wall.
Is that just a coincidence, or?
No, it's the way the sign, because the electricity coming out of your wall is a sine curve.
Oh.
So it just happens to fall into that information. Yep. So like whenever you're doing your calculations, that's the value you use just because it's easier than trying to use the variable curve because AC goes up and down constantly. So, all right. Now let's actually set up my integral and do the calculations for this. So are we doing the disk method or the washer or the washer method or the cylinder method for this one? We're going to do the washer because that makes sense for this one. We have it solved for x equals, and we're going around the y-axis or the shifted over y-axis. So my integral is going to be 2 times 0 to square root of 2 over 2. And then it's 2 pi r squared. And the r is 2 minus y squared minus 1 plus y squared. Okay. All right, so let's clean this up as much as I possibly can. Oh, it's not 2 pi r, it's just pi r squared. I had the other one in my head too. All right, so let's do this part in here real quick. So I've got 4 minus 4y squared plus y to the 4th minus 1 plus 2y squared plus y to the 4th. So I've got 4 minus 1 is 3 minus 6y squared and that's it. Because the y to the 4th cancel out. So I've got 2 pi, 0 to square root of 2 over 2, of 3 minus 6y squared dy. So if we do our quick integration for this one, I got 3y minus 2y to the 3rd. And we're doing it from 0 to square root of 2 over 2. The 6 divided by 3 is 2, so that's where the 3 went from down the bottom. So the nice thing is the 0 cancels everything out, so I don't have to worry about the 0 term. That's why we did the multiplying it by 2 using the symmetry in there, so I didn't have to deal with it twice. So we just have to put it in once. So 2 pi. Then I have 3 square root of 2 over 2 minus 2 square root of 2 to the third power. So we can do a little bit more cleanup on this one. Honestly, if you left it like this, I'm not necessarily marking it wrong. This part right there will become 4 square root of 2. Because I can pull out the square root of 2 squared. So, yeah.
How did you get the 2y to the power 3? Is that just simplified?
Oh, what? This to that?
That.
Yeah. So you bring down the 3.
Right.
So 6 divided by 3 is 2. Yeah. And actually, while I'm thinking of that, because when you said that originally, I'm like, wait, I did mess it up. That's over 2. Because I forgot that's 2 to the third, not just 2. Because I was canceling out the 2 and not where I was supposed to. So this right here ends up becoming 2 square root of 2 over 4, which is square root of 2 over 2. So my final answer is yeah, because there's because the 2 out of the top, that's the 2 square root of 2. And then there was the original 2 that was here that canceled out with the extra 1 down the bottom.
So if we left it as
If you had left it like this,
okay.
I might take a point off just because it's not totally simplified, but I'm not going to mark it wrong. Like, so that's the thing. It's like when you're going to see how this actually becomes really simple in a second. But if you just don't simplify everything down all the way to the end, but you've done all your integration and everything else correctly at the beginning, it's just like not simplifying a fraction. I'm just going to take off a point for it. So I got 3 square root of 2 minus square root of 2, which is 2 square root of 2 divided by 2, which is just square root of 2. So it ends up being 2 pi square root of 2 is my final answer. Yeah, so I said this one actually simplifies down to a nice single thing. Yeah, so this part right here, there's 3 2's down the bottom, 1 2 here. So that's where the 4. Because I took one of them. The square root of 2 to the third is 2 square root of 2. Right? Because there's 3 square root of 2's. So 2 of those make 2. So that's that one. And the one left is still the square root of 2. Then that becomes square root of 2 over 2. And then I did 3 square root of 2 minus square root of 2, which is 2 square root of 2 over 2, which is just square root of 2. And then it was times the 2 pi plus. Yeah. Now,
So the official answer is
2 squared. It's equals. That's equals 2 squared root 2 pi squared root of 2. That would be the final official answer for that problem. Now, the same thing would happen if you had the original problem correctly and didn't simplify it right. I still would just take off a point. So if you try to simplify and you mess it up, you still just lose the point. So. All right. Any other questions on number 1?
Could you explain again
Which part?
The ending reason.
So I got, all right, we'll just do it this way.
I really struggle with those two.
So I had, what was it? 2 pi, 3 square root of 2 over 2 minus 2 square root of 2 over 2 to the third. Right?
Yes.
Okay. So this part right here becomes 2 square root of 2 to the third over 2 to the third. Okay. Which is 4 square root of 2 over 8.
Okay.
Got it?
Okay.
Which is square root of 2 over 2. Okay, so now I have 2 pi, 3 square root of 2 over 2 minus square root of 2 over 2, which is 2 pi, 2 square root of 2 over 2, which is just 2 pi square root of 2.
Okay.
So, real quick, dumb
Yep.
question, my brain's dead. How did you initially come to your boundary between the square root of 2 over and 0?
Here. You can do this one of two ways. You can look at the graph, which is going between negative 7.707 to 707. Or you could do what I actually did. You can literally just set them equal to each other and figure out where they cross, which gives you the square root of 2 over 2. The only difference in this would have been if you had, instead of putting in square root of 2 over 2, you were putting in here the 0.707. This would have looked messier because of all the decimals. Yeah, it would have come out to be the same answer approximately.
But how is it only half if the like rotating points that you're going from -1? It's like
Because it's still, okay,
oh never mind, doing it 0. Okay.
you're still, well, yeah, the graphs, you're still rotating it. You're still rotating it over here. But the top and the bottom are identical. So rotating the top around is going to give you half of the whole.
And
No.
you mean like
From the x-axis, I broke that down. I broke it. So instead of looking from this point to this point, I'm looking from this point to this point, or from there to there, which is exactly half of the whole thing.
so this is a
This was a
yeah, so you have y.
yeah, because it's in terms of y. So rotating, if it's in terms of y, I'm rotating around the y-axis, or in this case, x equals -1, which is a shifted y-axis. We can use the disk method. If it was in terms of y equals, then I would have had to do the cylinder method. Yeah. All right. Next one. All right, so this one, we're looking at, this one's being rotated around the y-axis, and it's in terms of y equals. So for this one, since it's in terms of y equals, rotating around the y-axis, I need to do this in the cylinder method. So remember, the cylinder method was x times 2 pi, or times the height. And the height was the difference between the two curves.
So you said because it's in terms of y rotated around the y-axis, that's why you use the cylinder method?
Yeah, because we're looking at the lines going, we're looking at the equations from here to there.
Hold on,
That's okay.
can't see.
Yeah, that's why I was waiting. So we're looking at the line going up and down between the two.
Okay.
And if we're rotating around, it's going to make a cylinder.
Right.
So that's why I have to do the cylinder method for it. Where the other one, when I was looking at it, I was going this way.
Right.
And when I was rotating it, it's basically making a disc. Okay. So when we look at this one, we still need our starting and ending point. My starting and ending point are from there to there, which is 0 to 1. All right, so now that we have our heights, we just set up our integral for this one. So my integral is from 0 to 1. We can pull out the 2 pi because that's just a constant. And it's x times the 1 over 1 plus x squared is the top minus the bottom. All right, are we good with how we got the equation for it? When the height's not squared. So, because height wouldn't be squared in this case. We're not looking for the area of the disk. We're looking for basically the surface area of the cylinder. All right, so let's do the integral. All right, so let's distribute the x through. So I've got x over 1 plus x squared minus x squared over 2. Now, if we look at the x over 1 plus x squared, this is where that u substitution comes in really nicely. So we have, if we set u equal to 1 plus x squared, du is 2x. So we have 1 over u, 1/2. What's the integral of 1 over u? Yep. So we've got 2 pi. This is 1/2 the ln of 1 plus x. The x squared over 2, that one works out really easily. That's just x to the third over 6. And we're evaluating it from 0 to 1. So I've got 2 pi, 1/2 ln of 2 minus 1/6.
Going back to like the x3 over 6.
Oh, it's not, it's 8. You're right. Oh, no, that's 3. No, you're right. It was 3. Sorry. Never mind. It was 3. I was thinking back and stuff. 3, because you have to divide by the third. hearing myself back? Okay, better. So the 2 times 3 is 6. That's where the 6 came from down the bottom.
So you were just comparing 2 steps in that one.
Well, kind of. It was one third times x to the third, and the 6 is already down. The 2 was already down the bottom, so I just did 2 times 3. So yeah. Yep.
You can take constants out of the thing, but you're not plugging into them, right? So you can like take the 2 off the 2 and the half.
No,
You can't.
no. I can't until if it was the whole thing was to the 1/2, I could. But since the whole thing's not to the 1/2, I can't just pull out the 1/2 because the 1/2 isn't part of the 6th. I'd have to do something with that part too. Yeah, so like I can't just pull this 1/2 out.
Well, you can break up the 1/6.
Yes, but it's just easier to do it down here. So yeah, you could factor out a 1/2 if you want and deal with it that way. You could do that. It's just going to be easier to just do that in the next step right here.
You get 2.
Which 2?
Bottom 2.
That?
Yeah.
I plugged in 1. 1 plus 1 squared is 2. Yeah. Because I have to evaluate the 0 and the 1. And I don't have to do the 0 because they're both going to have to be 0. Yeah. Because it's 1/2 du, so that x became 1/2 du.
Right.
So now if we do our final step, you get pi ln of 2 minus pi over 3. Nope, you can leave it just like that. If you gave it to this decimal, it's fine. It's not the end of the world, but that's what you could leave it like that. It's just like the last one, leaving it as pi squared root of 2 over. It's as simple as you can get.
If we left it at the 2 pi 1/2.
I probably take off 1 just because you can easily divide them by 2, but it depends on my mood when I'm grading them at that point.
Just make sure you're in a very good mood.
It just depends on how I'm feeling at that point. But like I said, the vast majority of your points are coming from the integration. So it's when you're looking at this problem, making sure you set up this integral correctly, you have the right bounds, making sure you're doing your integral here correctly. That's what I'm looking for. Simplification at the end is like simplifying a fraction. If you lose, you might lose a point. Like that'd be the most you'd ever lose on a simplification. 10.
Okay.
So there's 10 questions. They're each worth 10 points. The only time they're ever not going to be worth equal points is if I tell you specifically this was worth 5 points and stuff like that. But if there's not, every question's worth the exact same amount of points. All right. We're going to skip number 3 for right now, just because I know I'm going to need time to go through 4 through 10, and 3 is very similar to this one. So if I get time at the end, I'll come back and do question 3. All right. So if you had a chance to look at chapter 7.5, this is what chapter 7.5 is. All it is how do you choose which method you're going to do? Okay. So whenever you're doing any integration, the very first thing you want to look for is, can you simplify? All right. Can you break it down in a way that's going to make your life simpler? That's in terms of foiling, like this multiplying things out, canceling terms out, trig functions, using trig identities. If you have things in terms of not sine and cosine, turning to sines and cosines. Maybe you'll be able to get rid of some stuff. That might make your life easier. Those are the first things you want to look for. Can you simplify the problem? And actually, that's something you want to look for throughout the entire problem. Every time you do something to it, can you simplify it? Okay, because simplifying is going to make your life a little bit easier. Once you can't simplify it down and you're stuck at that point, it's like, okay, I need to do something else. Can we do a U substitution? So the most obvious one is where you have an x over an x squared. It's like when you're looking at that, that's something easily recognizable that, yep, I could do a U substitution for that. Instead of doing more complicated stuff with it. Okay. So those are the very first two things. Notice I haven't talked about integration by parts or any of those things. Look at this stuff first. Saves you time. If those don't work, then we got to look at the other ones. If you can't read this, this is all literally in section 7.5 in the book, but you'll be able to look at the notes afterwards. I don't expect you to write everything down here. Trig functions. If it's in terms, these are the ones where these are all basically at the same time. So if it's trig functions like sines, cosines, tangents, secants, those type of things, look at the trig function at the identity rules and section 7.2, where we're looking at how to simplify those down and break those down. Rational functions, if it's a fraction, if you cannot do U substitution and it's a fraction, you most likely are going to have to do partial fractions, which we did on last Thursday. If it is a problem that has a product in it, multiplication, and we can't simplify it, we can't do U substitution, you're probably going to have to do integration by parts. If there's square roots or radicals in them, you're probably going to have to do that trig substitution, unless we can do U substitution. All right, everything goes. Look at U substitution before you try these. Okay, so we had partial fractions, we had integration by parts, we had the trig substitution rules, and then we had just using the trig to simplify things down, like the sines and cosines and tangents and secants. Okay, so those are really the rules that we have. Every problem you look at, that's the thing you want to look at. It's like, okay, what process am I going to have to use to solve this first? So let's look at them. Now, I did not put any special, like tricky ones in here. So they're all ones that you're probably going to have to do one of those things on. But we're going to ask the same questions. Can I simplify this one? Is there any way to simplify an ln of x and an x to the fourth? No. If I do a U substitution, it's probably really not going to help you in this situation. Because I can make u ln of x, but then my du is going to be 1 over x, and I don't really have an x in the bottom anyway, and it's going to introduce a fraction in there, which I really don't want fractions in. So let's not do that. So this one, what is this one? What do we have? Yeah, this one's a product. Products are integration by parts. So we have our u du and our v dv. All right, so which one am I going to make my u? Okay. And that means my dv is x to the fourth. So my du is, what's the derivative of 1 over, the derivative of x is 1 over x. And then my v is going to be 1/5 x to the 5th. So remember the, what is lathe? Yeah. Logs, inverse trig, trig, and then exponential. So exponential is the very last. Very good. She's been studying, or she's really good at memorizing mnemonics.
Yeah.
All right. So now we set up our integration by parts. It's uv minus the integral of v du. So u is ln of x v is 1/5 x to the 5th minus the integral of 1/5 x to the 5th times 1 over x dx. So this integral right here, we can clean up a little bit. It's just going to be basically x to the 4th over 5. Because I have x to the 5th divided by x is x to the 4th. So I have 1/5 x to the 5th ln of x minus x to the 5th plus c.
I got something else.
What'd you get?
I got ln x. So the first part I got the same, but after the minus, I got 1/25 x to the 5th. Does that make it different?
Oh, you're right. I did my division wrong. You're right. You're right. No, you're fine. I did it as the, because this is where your derivatives and your integrations screw up things. All the little mistakes that you don't want to make on the actual test. Because what I did is that when I brought the 5 down, I left it up top. And then I canceled up the 5. Which that's why I was looking at like, it shouldn't just cancel out. So just always ask. Oh, quick little thing on how I grade the tests. So when I grade your tests, I don't grade one test at a time. I grade a question at a time. So I grade everybody's question 1, everybody's question 2. This way it's consistent, and I'll see if I made a mistake. Because if I catch a mistake as I'm going through, then I fix that question as I go through. So it won't ever impact anything. That also means that I really can't give you back your test until everybody takes the test. So please, for all intents and purposes, make sure you're here on Thursday, and then I'll be able to give everybody back their test on Tuesday. Because if I have to wait to test somebody, then I can't give anybody back their test because I can't grade them that way. It also keeps things consistent when I'm grading it because I don't change how I grade it from question to question. So. All right. Next one.
So just before you, those X, you can down.
All right. So this one is a definite integral. So once I get my final answer, I just have to plug in the 0 and pi over 3 to it. Don't worry about like carrying the 0 and the pi over 3 to every integral you write through the problem. You can just do the integrals and then add that at the end. Just don't forget about it. So what do we got to do for this one? Yes, this is also going to be parts. Notice I did say these were in order. So they will not be in order on the actual test. So this one is a product again. We have two things that are multiplied. There's no real way to simplify e to the 30x and cosine of x. There's no way to really do a u substitution for this situation because they're kind of different things. So we are going to have to actually do integration by integration by parts. So I'm going to have my u du and my v dv. So what is u in this case? Yep. And my du or dv is going to be e to the 3x. So my du is going to be negative sine x dx. And then my v, almost, 1/3. 1/3 e to the 3x, because you have to do the implied u substitution. Because u is in essence 3x. You have to do that u substitution for it. You just don't typically have to write it out. So u is 3x, so when you take the derivative of that, you get 1/3 du equals dx, so that's where the 1/3 comes from. And then the e stays the same, it's e to the 3x.
Just as my answer is like start with you as e to the 3x.
So you could, but remember there's and actually on this one,
And I'm doing the chain rule and then realizing that it's the same equations.
yeah, I was gonna say on this one, I don't think it actually will matter. If you screwed that up. But remember, the exponential is always the very last thing you're going to choose. So it's always going to be dv unless you have two exponential functions. And if you have two exponential ones, odds are you can try to somehow put them together. So, all right. So I've got cosine x times 1/3 e to the 3x minus the integral of 1/3 e to the 3x times negative sine x dx. All right, so we've got to do our integral again. We do have to do the integration by parts again for this one, so we're going to do integration by parts on this part here. So again, same thing. So my u is now negative sine x. So my du is cosine x dx. No, negative cosine x dx. And this one is, now, you could have actually pulled out your 1/3 if you wanted to. It's not going to make that big of a difference. This just ends up being 1/9 e to the 3x. So we now have 1/3 e to the 3x cosine x minus negative sine x 1/9 e to the 3x minus the integral of 1/9 e to the 3x times negative cosine x dx.
Sorry, I feel like I keep interrupting you. But
You can
what-
keep interrupting me all you want.
So in the middle of your last line where it says negative sine x
Yeah.
1/9, why is that not 1/3 and then the next one is 1/9?
Because it's uv. That's still v. If you had pulled out the third here, the 1/3,
Right.
this would have just been 1/3 multiplied by the 1/3 that was in front. It's still going to come out to be the exact same thing at the end. It just depends on where your fractions are. But yeah, that's going to be 1/9. I'm going to rewrite the bottom piece in a second anyway, because I have to do the next parts. All right, you should have noticed that this part at the end is almost like the original problem, which we're going to clean it up a little bit so you can see that. 1/3 e to the 3x cosine x plus 1/9 e to the 3x sine x. And then you have plus, actually it's minus. Minus, it's minus because of this. That negative, that negative, and that negative makes a negative. As I said, I'm like, nope, I forgot the one in front. I caught that one. And it has to be, it has to be negative because when you pull it over, if it's not a negative, it'll end up canceling itself out. So e to the 3x cosine x dx. So you can now bring that part over and you're dividing the whole thing by 2. So your final answer is 1/6 e to the 3x cosine x.
Well, what's that one?
It's because of the way I did it with the thing. It's technically that should have been out in front of the whole thing.
Oh, so you're pulling the one like that. the whole-
Oh no, I got it. Hold on. Never mind. Never mind. Hold on a second. Where's the first one? It was the integral of e to the 3x cosine x, right? dx. If I add 1/9 to that, you get 10/9.
Yeah.
So you're going to divide this side by 9/10.
Okay.
Yes.
Okay. Yeah.
So you divide this whole thing by 10/9, which is multiplying by 9/10. So actually, I'm going to write that way because that's a lot easier to write. You're multiplying this whole thing, this whole thing, by 10/9. So we get 10/27 e to the 3x cosine x plus 10/81 e to the 3x sine x. Huh?
No, but I see it differently and go to you from right on. You don't put in a glitter pen. Doesn't need a glitter pen.
Oh yeah. Speaking of glitter pens, I don't care which you take your test in, unless as long not glitter pens, it better not be fluorescent ink. That is the only ink that I can't stand. I write everything in pen. I do all my work in pen, but I cannot stand fluorescent ink. It just hurts my eyes to look at. And I had this person do all their work in fluorescent pink because she loved pink, and it literally drove me nuts. So I literally told her like 3 times to stop, and when she wouldn't stop, I just started marking everything wrong and handing it back to her. She eventually got the message and gave me an actual like pencil or black pen. Because it hurts my eyes to look at it. So don't do fluorescent pink. Unless you really want a zero. Yes.
Is that 10/81?
81, yes.
Was it last 6 and after 10/8?
Huh?
Oh, yeah. That's what it was.
10/81.
Yeah, 10/81 e to the 3x sine x. The e to the 3, that's the thing about exponentials, they never actually change. They always basically stay the same.
That's in 10/9 and 10/2.
This, 10/9.
Bottom one. Bottom right.
That,
No, bottom right.
that,
Yeah.
10/27. Because it was 1/3 times 10/9.
Why is this very fine?
It is. It's 1/3 times 10/9. So it's 1 times 10 is 10, 3 times 9 is 27. Remember, when you multiply fractions, you just multiply straight across.
Nine over 10, which is
Did I do 9/10 instead of 10/9? I did. It's fine. The nice thing is that's not the question on the test. It's different numbers anyway.
For that.
wait, isn't it
Corresponding
supposed to
one,
be
you mean?
9/10?
Yes, it's supposed to be 9/10.
Okay.
I did not. do the-
No. Yes. Yes. It should have been multiplied by 9/10, not 10/9. So my fractions are wrong. I'll fix it later.
Different integral?
I'm trying to get through the rest of the questions.
Well, some stuff cancels out this
So it's 9/10 instead of 10/9. I know it is. Because the 9s cancel out.
way. And then 9.
So this becomes 1/3 times 9/10 is 3/10. And this just becomes 1/10. And then we put in pi/3 to everything. What's a pi/3? This is why I make my reviews harder than my actual tests. All right, so we're evaluating this from 0 to pi/3. So I got 3/10 e to the pi. Cosine pi/3 is what? 1/2? Yeah. 1/10 e to the pi. Sine to the pi/3 is square root of 3/2. Right. And we actually cannot avoid the 0 because cosine of 0 is not 0. So 3/10 sine is though, so we don't have to worry about that part. And then I have e to the 0, which is 1, so I don't have to worry about that one. And cosine is 1, so I don't have to worry about that one. So it's minus 3/10. So I've got 3/20 e to the pi plus square root of 3/20 e to the pi minus 3/10. And I'm not simplifying that anymore. You could pull out the square root of the e to the pi, and I'm not doing it. I'm not simplifying that one down anymore. Huh? Yes. All right. Next one. I had to choose that one to be the one with the actual definite no-go part. All right. Next one. So we got tangent to the 4x and secant squared x. So the question is, so now this one is my trig ones, right? So we have to use some kind of identities to work this out. All right, so if I change which one am I going to make u? Let's start with that. Okay, so if I make tangent u, what's d? Secant squared dx, which I have. So this integral becomes u to the 4th du. So I end up getting u to the 5th over 5. So it's tangent to the 5th x over 5 plus c. That's it. I know after the last one, I was like, wait, this is easy. Remember, all questions are worth 10 points. So there is some strategy that comes into play in which you get. If you're going down a rabbit hole in a problem, Move on. Okay? Or go through and look at the problems and say, oh, I know how to do this one real quick. Get it done. And then go back and work at the problems that you're going to struggle on and are going to take you some time. Okay? Every question's worth the same. So this question right here is worth the exact same as the last question. Last question was worth a lot more work. So it's a matter of use your time effectively when you're going through and doing it. Okay? All right, next one. Sine to the fifth x, cosine squared x. So which one do I want to make u in this one? Yes. Because I have, remember, you always want to make, you want the odd one that you're going to pull a piece out of it. So we're going to change this problem to sine to the fourth x, cosine squared x, sine x, dx. So that piece will be my du. So u will be cosine x. So du will be sine x dx. So now what do I do with that sine to the fourth?
1 minus cosine.
Yeah. So that's 1 minus cosine squared x squared.
I think it's negative sine x.
You're right, Liz. We pull out the negatives. So we just pull out the negative sign. All right. So we got negative the integral of 1 minus u squared squared times u squared du. So I've got 1 minus 2u squared plus u to the fourth times u squared. So u squared minus 2u to the fourth plus u to the sixth. All right. So take my integral of this. So I've got negative u to the third over 3 minus 2u to the fifth over 5 plus u to the seventh over 7 plus c. So negative 1/3 cosine to the third x plus 2/5 cosine to the fifth x minus 1/7 cosine to the seventh x plus c. I ran out of room. The cosine to the seventh is not really on the bottom. Each question has one full page plus the entire back of the page, plus I'll have scrap paper. So you have plenty of room to write on your test.
Minus 1/7, right?
Yes.
That's minus 1/3.
Yeah, minus 1/3 plus 2/5 minus 1/7.
And the plus C at the end.
It's always plus c. Even if it's minus, it's always plus c. Because the constant can be anything. And we don't know what it is, so you always just do plus c. All right, 3 left. Number 8. So I got 1 over x squared, square root of x squared minus 16. So in this one, we have what? Can I do u substitution? No. Cannot do u substitution. So since we can't do u substitution, I have to do my trig substitution for this one. I have to do my trig substitution for this one. So what am I going to make x? Is secant? Okay. That's what that's literally what I was just looking up.
The rule is, it's x squared minus a squared.
Is a secant.
Yes, square root of the value.
Yeah.
Or a.
Yeah, just it's because you're actually it's not x. It's you could use u. It doesn't matter actually. You could use u. You could use theta. You could use anything except for x. Don't use x. All right. So 4 secant theta is there. So dx is what? 4 secant theta. That's fine. Okay. So now my square root of this becomes, is it just 4? No, 4 tangent. Let's see. So we got 16 secant squared x minus 16. So secant squared x minus 1, which is tangent. So we got 16 tangent squared x or theta. So that becomes 4 tangent theta.
Yes.
It's 4 secant theta squared because we're replacing the x with secant theta. All right, so I've got 4 secant theta tangent theta over 16 secant squared theta for tangent theta d theta. So that top piece became that. So that was that. And then the x squared became 4 secant theta squared, which is the 16 secant squared theta, times the 4 tangent theta, which was my square root. So now we can simplify this a lot, actually. I have the tangents can cancel out, the 4s can cancel out, and one of my secants can cancel out. So I end up having 1 over 16 secant theta, d theta. So I can pull out the 1/16th, and the 1 over secant is cosecant. All right. Yeah, this one can have to be nice. All right, so let's do the integral of that. So this is 1 over 16 sine theta. Now we need to go back to x's. So if we remember, my x was 4 secant theta. So if we look at my wonderful little triangle here, so if that's theta, secant was hypotenuse over adjacent. So x over 4, and then that's the square root of 4 or 16 minus x squared. Of course, no, it's x squared minus 16, right? Yeah. Because remember, the side piece is always the square root, the piece that's missing. So sine theta is square root of x over 16 divided by x. So it's 1 over 16. It's square root of x squared minus 16 over 16x plus c. Is my final answer. Yeah, let me give everybody a second to write this down. All right.
You get x squared minus 16 in the next slide.
Because sine is opposite over hypotenuse. So sine of theta is opposite, which is that over that. That's where I got that. And the 16 just came from the 16 that was in front.
Professor, how come we don't include sine in the,
Because you're actually finding what sine of theta is. So you're actually you're not replacing theta, you're replacing sine of theta. If you had a problem with just theta left, then you're going to have the arc sine or arc cosine, whatever happens to be, whatever function you're using in there. All right. Let's do 10. Well, actually, we'll do 9 first. All right. So this one. If we look at this one, what do we got to do? We have to do long division, actually. All right. So the nice thing is this long division is not very long to do. So we've got x squared plus 3x plus 2 divided into 3x squared plus 6x plus 2. How many times x squared can go into 3x squared? 3 times. So I got 3x squared plus 9x plus 6. Subtract them all. And I'm left with negative 3x minus 4. So my integral is from 1 to 2 of 3 minus 3x plus 4 over x squared plus 3x plus 2 dx. I told that negative sign.
Okay, yeah.
I just didn't feel like dealing with the negative signs when I'm going through and doing the partial fractions. It doesn't make a difference if you left the negative sign in there or not. All the work's going to be the same. It's just one less thing that I can forget to write. All right. So now we have to do our factoring of the bottom. So this is x plus 1, x plus 2. So I'm just looking at this. I'm going to ignore the 3 for a second. We'll deal with that once I get my final integral down. So I've got 3x plus 4 over the x plus 1, x plus 2 equals, and it's going to be a over x plus 1 plus b over x plus 2. So I can write 3x plus 4 equals a x plus 2 plus b times x plus 1. Huh?
And two.
Yes, those are the two I'm going to plug in. So now I have to do my little trick I showed you by plugging in some numbers. So we're going to make x equal -2, which will get rid of my a. So I've got -6 plus 4 is -2 equals -b. So b equals 2. And then if I plug in -1, I get 1 equals a. So was it 0 to 1, right? 1 to 2. Remember, there was a negative sign out in front of this whole fraction thing in a second. I'll show you in a second. That negative sign right there is what makes them both minus. All right, so now I do my integral. So I've got 3x minus ln of x plus 1 minus 2 ln of x plus 2. And we're evaluating that from 1 to 2. So if I plug in 2, I get 6 minus ln of 3 minus 2 ln of 4 minus 3 minus ln of 2 minus 2 ln of 3. So I've got 6 minus 3 is 3 minus ln of 2 plus ln of 3 minus 2 ln of 4. And yes, you can simplify that down a little bit more by using the log rules to put them all together. No. So I had negative ln of 3 here, and then plus 2 ln of 3 here. Because of the minus sign. Oh. 6 minus 3.
Oh, okay.
Yeah.
That's too long.
I caught that after I said the other one. I'm like, I got the right that one there, and I screwed up that one. Yeah, 6 minus 3 is 3. Yeah, if you want to simplify, it would end up being 3 plus ln of 6 over 16, which is 3 over 8. Because 2 times 3 is 6. Ln the fourth is 16. So yeah, that would end up being what it's going to, that would be the final simplified answer. Because addition becomes multiplication, and subtraction becomes division, and the new number in front becomes an exponent.
How is it on for?
That's the 2 ln 4 from up here.
Oh, we're not subtracting.
Yeah, it is. It's minus 2 ln 4. I can't subtract that from the other 2 ln's. There's no other ln of 4 in this problem. The only one that I could put together was the ln of 3 because I had 2 of those.
Oh, wait. I didn't.
It'd be 6 over 16, which is 3 over 8. All right. Last one. And I'm not going to have time to do number 3, but that's fine. I'll do that up tomorrow and have the notes there for you. All right, so this one. Nice thing is it's already factored. I don't have to do long division or anything else on this one. I just have to set it up correctly. So this becomes a over x minus 1. And then it's bx plus c over x squared plus 9. So remember, when you have a quadratic, you have to have the bx plus c there. You have to have a linear term on top. So we end up having a times x squared plus 9 plus bx plus c times x minus 1. So I've got so if I plug it, so this one, the only one I can actually plug in is 1. Okay, that's the only number I can actually plug in to help me get anything out of this. So if I plug in x is 1, that's going to cancel out that part there. And I get 10 equals 10a, so a equals 1. So I now know what A is. So now we kind of got to FOIL this one out and see what's left over and see if I can work on some other stuff. So 10 equals ax squared plus,
You immediately want to plug in A.
yeah, that's what I'm going to do actually. And then 1 times 9 is 9. So yeah, I'll make my life a little bit easier. And then I have bx squared minus bx. And then I have c times x is plus cx. And then c times 1 is negative c. So I can bring the 9 over. So 1 equals x squared is b plus 1. And then the x there is c minus b, x minus c. So, is there an x squared term? So, okay, let me take a step back before I did that. Everybody understand how I got from here to here to here? Okay. Step 1, just multiply. I already knew what A was. A is 1. So that's x squared plus 9. Bx times that, I just FOILed this. Bx times x is bx squared. Bx times negative 1, negative b. C times x, c times negative 1. Okay? That's it. Now, I brought the 9 over. That's where the 1 came from. Because that was the only number that was left here and makes my life a little bit easier. Then I've got the x squared and the bx squared. So that's where b plus 1 comes from. Because if I added those together, I get b plus 1. The x, I have c minus b. I could have done negative b plus c. I just wanted the negative sign though. And then the negatives. Okay? All right. Now we got to figure out what the letters are. Now, you can go through and do this whole complicated thing out. What we can just look at. Do I have an x squared term over here? No. So this has got to be 0. So what's b? B has to be negative 1. It's the only number that would work there. Okay. And C, so that right there has to be that, right? So C also has to be negative 1. And we can check by looking at that one to make sure it works. What's negative 1 plus 1? No, negative 1 plus 1 is 0. And there's no x term, so it works. So I've got A is 1, B is negative 1, and C is negative 1. All right, so everybody to that point? Okay, so now we can write our integral. So my integral was, it was 1, right? Yeah. 1 over x minus 1 plus negative x minus 1 over x squared plus 9. Because they were both negative 1s. Yes. I think that's right. Yeah. Because A was 1, they were negative 1. So yeah, that should be right.
Thinking about the previous problem.
I'm going to do that in a second anyway, actually. All right. So now the next thing we have to do is break up that. So I have 1 over x minus 1 minus x over x squared plus 9 minus 1 over x squared plus 9 dx. All right, so now we've got to do our integral. So 1 over x minus 1 is just ln of x minus 1. This part right here, I've got to do my u substitution on. So u is x squared plus 9. So du is 2x. So 1/2 du equals x dx. So I've got 1/2 and then 1 over u. So that's 1/2 ln of u. So minus 1/2 ln of x squared plus 9.
I think you want to see how we got that.
This type of stuff right here, I almost consider implicit use substitution. You should know how to do it. So if you don't write that down, as long as this works out right, you're fine. The downside is if you didn't write this down right and I can't figure out where you screwed up, then I can't give you the points. So if you're not going to write it down, don't screw it up. All right. What's that crazy rule? It was 1 over a arctan of x over a. And a was the square of that number there. So in this case, a is going to be 3. So it's 1/3 arctan of x over 3 plus c. So I would suggest having that rule written down in your note card because you're probably going to see a question like that. Which one? That's just a rule. That was one of those rules that we did in class on Thursday. It was so it's if it's you can't integrate it because it's the 1 over x squared plus 9. So and we don't have a square root, so I can't do the trig substitution or anything else like that. So that was just one of the rules that I gave you. It was 1 over a arctan of x over a. And the a is the number that's in that part. So the a is the square root of 9, which is 3. Because it's x squared plus a squared. That's what I said. That's just one of those ones that I would have written down unless you know it. All right. That's it. I'll post this stuff up there tonight when I get home. I will post the explanation for question 3 tomorrow morning because I didn't get a chance to do that one tonight. So I'll write that one out for you. So I'll have that one posted up tomorrow morning. Show all your work. I give lots of partial credit and stuff in there. So it's not like if you have the answer wrong, I mark the whole thing wrong, you lose all 10 points. So show me your work. The work is going to show me if you understand what you're doing or not, and I give points based on that. So, oh yeah.